talk about the first derivative and what it means in regard to the graph. So when we know that f prime of a is positive, we know that that means the function is increasing at a. One thing I noticed on the test, some people were a little bit careless with the language. So if I say the graph is increasing, the proper way to say that is f of x is increasing at x is equal to a. What's kind of wrong is to say f of a is increasing. Like f of a is a value, and we're not really the value is not really increasing. Like it kind of is, but that's just like poor notation. So just be careful with how you word that. F of x, is increasing at a. We know that if f prime of a is negative, then f of x is decreasing. If f prime of a is 0, we know that f has a horizontal tangent line. And then if f prime of a is undefined, then that means f of x is non-differentiable at that value. And of course, if f is non-differentiable, that could mean several different things are happening there. For example, we could have a corner or a cusp. We could have some sort of discontinuity, whether it's a jump, whether it's a hole, or vertical asymptote, or we could have a vertical tangent. So that's just going to be a quick review of last unit stuff that's going to show up again and again. And then the other thing I want to review is just how we write out intervals of increasing and decreasing. So if I gave you a graph, you've done this multiple times before in other kind of classes, where if I have the graph here, we should be able to identify intervals of increasing or decreasing. Sorry guys, I hit a button. When it comes to intervals of increasing and decreasing, we are always going to use interval notation. So like when I say the graph is increasing, this particular graph is only increasing in that one section of the graph. Also, when you give your intervals, we're going to say that the graph isn't technically increasing or decreasing at high points on the graph. So not only will we use interval notation, but we're also going to just use parentheses. For example, this graph would be increasing on the interval from negative infinity to negative 4, and is decreasing. So when I look at where this graph is decreasing, there is a horizontal tangent at negative 1. There's a jump at 1, and there's a corner at 2. But if I'm talking about where it's decreasing at, it starts decreasing at negative 4. Negative 1 is horizontal for that split x value instant. It decreases all the way to 1, and then it's also decreasing from 1 to infinity. There are some like mathematicians and like if you go to college math professors who would argue that this function is increasing completely from negative 4 to positive 1. It is what we call in math monotonically decreasing. But in AP calculus, we're going to keep that separated as two separate intervals. So negative 1 is just a brief moment where it's horizontal. Everywhere else, the graph is decreasing. So what we're going to look at, instead of looking at a graph, I'm going to give you, I'm going to kind of jump to the example and then come back to it. I'm going to give you a function and say, hey, find where this function is increasing and decreasing. We're going to use calculus to figure that out. The first thing that we need to know, though, before we find intervals of increasing and decreasing, is something called a critical number. Sometimes we'll also call this a critical point. Those words are interchangeable. And a critical number or a critical point is somewhere on the graph of f of x where one of two things could be happening. The first case where we have critical points is when the first derivative is equal to 0. The second place where we have critical points is when the first derivative is undefined. Both of those locations on the graph is where we have these things called critical points. They do have that name because we will say they are critical in regards to like what the shape of the graph looks like. A lot of students always remember to find where f prime is equal to 0. I often find students forget the case where a critical number is also where the f prime is undefined. We'll do this algebraically, but just so you can kind of see it a little bit visually. Here's that same graph that we did previously for the intervals of increasing and decreasing. The critical points for this one we often define by the x-coordinate. We have two horizontal tangents at x is equal to -4 and -1. We also have two places where the derivative is undefined. We have the derivative is undefined at 1 because it's a discontinuity. The derivative is also undefined at 2 because that is a cusp on the graph. So we do have two types of numbers in these critical points. One where the derivative was equal to 0, and one where the first derivative was undefined. So the first thing I want to do is just before we talk about intervals of increasing and decreasing, I first just want to find the critical points. So let's find the critical points algebraically. This is how more of the question is going to look like in calculus, where we don't have the graph in front of us. So we do need to find it using our algebra skills. So if you have a question that tells you to find the critical numbers or the critical points of a function, that's basically asking you to find two things. It wants you to find, again, where the derivative is equal to 0 and where the derivative is undefined. To define this out a little bit further for you, when we talk about something being undefined, that's often when the denominator is equal to 0. If that helps you remember when it comes in regards to the derivative being undefined. And then when y prime is equal to 0, then that's just setting the problem equal to 0. Oftentimes, if it's a fraction, we'll end up just setting the numerator equal to 0. So if I need to find the critical numbers, the first step is going to be to find the derivative. And of course, this is why the rules are important. So all the rules you've learned can apply to this. Could either do the quotient rule or the product rule with the chain rule. Since this denominator is a pretty easy derivative, I'm going to go ahead and just do the quotient rule. So I have y prime is equal to, I have low d high less high d low, draw the line down below, the bottom square will go. And so that's the unsimplified derivative. And I often tell students for these types of problems, like the calculus is over. The rest of the problem is just like simplifying and solving. So I'm going to go ahead and simplify this because we do want to find when it's equal to 0, and this is kind of messy to solve right now. But I am going to go ahead and simplify my derivative. So I have y prime is equal to, I'm going to leave that denominator as is right now. And so I have 4x squared plus 8x minus 2x squared. Combining like terms, 4x squared minus 2x squared is 2x squared plus 8x all over 2x plus 4 squared. And then what I want to tell you is your life is going to be a whole lot easier if when you have a derivative, you just get used to like writing it as a single fraction and then also in like factored form. So you can clearly identify the critical numbers. It will also be easier for you in the long run, and you'll kind of see what I mean when we find the intervals of increasing and decreasing if your answer is fully factored. So I would finally write my first derivative. This numerator can factor out a 2x, leaving behind an x plus 4, all over this 2x plus 4 squared. So we found my derivative. And now at this point, I do want to go ahead and find my critical numbers. And again, the critical numbers are going to show up when that first derivative is equal to 0 and when the first derivative is undefined. So when I set y prime equal to 0, like we're going to solve this equation, setting the equal to 0, that denominator just kind of multiplies and goes away. So we're really just setting the numerator equal to 0. And this is why factoring helps, because when that numerator is factored, you can easily see what those critical points are. So I have two critical points. One of them is at 0, and the other one is at -4. The other place where we have critical points is when the derivative is undefined. This first derivative will be undefined when that denominator is equal to 0, because we know in math we cannot divide by 0. We'll take the square root, the square goes away, minus 4 divided by 2, I get x is equal to, I'll go and spell it out, we get x is equal to -2. So if I'm looking at this graph, it has 3 critical points or critical numbers. And what those represent is those are going to be key points on the graph. So those could be places that the graph changes direction on. They might be asymptotes, they might be holes, they might be like in the cubic function where it just kind of flattens out a little bit. But those are going to be key points on the graph of the of this particular function. Questions on how I found the critical points of that graph? And I will say often we'll rarely find the y values of the critical points. We'll pretty much stick to just finding the x values. So how are critical points used? We use critical points to find the intervals of increasing and decreasing. And there's 2 steps to finding the intervals of increasing and decreasing. The first step is I put already done here, because the first step is going to be to find your critical points. And those are going to be where the derivative is, of course, equal to 0 or undefined. We found the critical points already, and I already forgot them, so I'm going to go back and look at them. All right. So I did save some time by choosing the same problem, but we found the first derivative. We used those to find the critical points. So we have critical points at 0, -4, and -2. And we're going to use those critical points to create a sign chart. Now I do want to pause and talk about sign charts. There's lots of different ways to make sign charts in math. I will say I have my way, and I do think that my way is the best way just because you're least likely to make a mistake. But we have to make a sign chart because basically we want to figure out when the derivative is positive and when the derivative is negative. The other thing about sign charts, AP College Board is very particular about them in that a sign chart is not considered like an answer. You can use a sign chart to form your answer and to kind of justify your work, but you cannot just have an answer that's a sign chart by itself. So the second step, I do have sign chart as obviously a step, but it's really just like a step that's going to give us our answer. So what do I mean by a sign chart? A sign chart is basically a number line, and we're going to use that number line to figure out when the derivative is positive and when the derivative is negative. We know a positive derivative means the function is increasing. We know a negative derivative, the function is decreasing. So on my number line, I'm going to go ahead and put my critical points. I do want to put them in numerical order. So like -4, -2, and 0. And then in the column, I'm going to list my factors of y prime. And this is why factoring is kind of important. The order won't matter, but I have 2x as a factor, x plus 4 was a factor, and then 2x plus 4 squared was also a factor. And then the last thing I do, and I'll explain why I do this really right now, is I put a little vertical bar underneath the critical point from its corresponding factor. So for example, the factor of 2x gave me 0, so I put like a little vertical bar here. The x plus 4 factor gave me -4, so I have a vertical bar there. And 2x plus 4 squared has a vertical bar there. The reason why I put those vertical bars there is it ends up speeding up the process, because the sign, whether plus or minus, can only change for each factor across its critical point. So for example, the 2x on one side of the line is going to be positive or negative, and then on the other side of that vertical line, it will be positive or negative. And we just want to plug test points into each interval. I do tend to do the easiest section first. So when I'm looking at these 3 factors, that bottom one, 2x plus 4 squared, well, if I square something, it's always positive. So I know that this bottom factor, no matter what, is going to be positive. So I go ahead and fill those in. It was an easy part. Now let's go ahead and think about 2x. So 2x gave me 0. So I want to think to myself, okay, a number to the left of 0, 2 times that number, is it going to be positive or negative? And you can pick any number. So I might say like -1. 2 times -1 is negative. So I know that everything to the left of 0 will be negative. Plugging in a number bigger than 0, 2 times a positive number is going to give you something positive. Notice it can only potentially change signs across that vertical line. And then for x plus 4, so a number less than -4, just think to yourself, I don't know, -6. -6 plus 4 is negative, so this interval is negative. Something bigger than -4, 0 is an easy one. 0 plus 4 is positive, so I know everything to the right of -4 would be positive. And then where we use this, so these are the factors of y prime. I can now figure out what y prime is overall. So like in that first column is what's happening when you're less than -4. Well, I have a negative times a negative divided by a positive. Well, a negative times a negative divided by a positive, overall this derivative is going to be positive. Next column, I have a negative and 2 positives. Well, if you only have one negative, it's going to be a negative interval. Third column, a negative times a positive divided by a positive, negative. And then this last column, all positives, so we know that this final interval is positive. And again, what we have found is we have determined the sign of the first derivative. I'm not done, because again, sign charts cannot count as your final answer for AP Calculus. But are there any questions on how I created that sign chart before I write down the final answer? All right, so your final answer, you do have to justify your answer like we've been doing. So it's asking to find the intervals of increasing and decreasing. So I have first, this is the function y. So I can say y is increasing on, and it's increasing when the first derivative is positive. So I know it's going to be increasing from -infinity up until -4, and then also increasing from 0 to infinity. Still want to justify my answer. How do I know it's increasing there? It's increasing there because y prime is greater than 0. And then when is it decreasing? I do something similar. Y is decreasing on the interval. So from -4 to -2, union -2 to 0. How do I know it's decreasing there? Because y prime is less than 0. That will be your final answer. Again, you can't just stop at the sign chart, which is a common mistake. You do actually have to go back and finish the question that's being asked, and in this case, justify your answer. Questions on that?
Why did you do like a union between the like two -2's instead of just -4 to 0?
Good question. So the reason why is that -2 is a critical point. So there could be two things that's happening at that -2. It could be a horizontal tangent, which means it will kind of be flattening off there for just like a split second, so it wouldn't technically be decreasing there. In this case, it's actually an asymptote because x can't be -2 in the original function if you're looking at that denominator. So like, would you be wrong if you said it's decreasing from -4 to 0? Technically not. It's just not like the best version of that answer. It's really going to be nicer for you, and I'll show you why when we look at the graph, to kind of just keep each interval separated, if that makes sense.
Thank you.
And so why? So like normally these questions will definitely be no calculator. Like we know it's 2020. You can type this function into the calculator and see it. I did go ahead and do that just so you can kind of see the graph. I think it's nice to be able to see. So here's the graph of that function. And you can see, well, yes, it is decreasing. Or let's do increasing. It is increasing from -infinity to -4 and 0 to infinity. And we can also see that it's decreasing from -4 to -2 union 2 to 0. So this is another kind of reason why I want to keep those intervals separated, because technically the graph isn't decreasing at -2 because it's not even existing at -2. Where we're going to add on to this tomorrow, I'm going to use the same function. We'll talk about intervals of concavity. How can we use the equation of the second derivative define where the function is concave up or concave down. To finish out today's notes, like they're not always going to be this easy. I mean, this really is kind of an easy topic. I think where students start to have trouble though is when I start doing functions with trig in it. So this is going to be the last example that we do. So I have f of x is equal to 12 plus 4x minus 3 tangent of x. For trig, I will always give you an interval. The AP exam will do the same thing. You know trig is repetitive, it's periodic. So you often want to just talk about like what is it doing between some starting point and some ending point. So again, if it says find the intervals for increasing and decreasing, to yourself, that should kind of tell you that there's a process you need to go through. You need to find the derivative. You want to use that derivative to find the critical points. And then you want to use those critical points to create a sign chart. There are some tips I want to give you. So let's go ahead and find the derivative of this one. So I have f prime of x is equal to, the derivative of 12 is 0, the derivative of 4x goes to 4, minus 3 is a coefficient, and the derivative of tangent is secant squared of x. Now this equation of the derivative is perfectly fine to use. Like you can set this equal to 0 and you can make a sign chart with it. For me though, if I left it like this, it's really hard to make a sign chart when you don't have like clear factors. I also think it's hard to deal with dealing with reciprocal trig functions. So like dealing with secant and cosecant is difficult. I also find dealing with cotangent and tangent kind of difficult, especially when we start have to talk about when it's positive and negative. So my advice to you, when you have a derivative with secant in it, or cosecant, or tangent, or cotangent, is to first put everything in terms of sine and cosine, and then write it as a single fraction. And what I mean by that is we all know that secant squared is the reciprocal of cosine squared. I also like writing it this way because we know critical points come from where the denominator is equal to 0, and with writing it as secant, you don't often see a denominator there. And then to make your sign chart easier, I recommend writing this as a single fraction, so basically get a common denominator. So if you're looking at this, the common denominator becomes cosine squared. And the numerator, we multiply that 4 over 1 by cosine squared over cosine squared. So your numerator becomes 4 cosine squared minus 3. And so that is the equation I'm going to use. And you might look at that and say, Mr. Brown, that looks way more complicated than 4 minus 3 secant squared of x. And I might agree with you, but then I also know it's a lot easier to deal with cosine when I start thinking about when is it positive and negative. And also when it comes to solving equations, cosine is just a little bit easier to use. So we found our derivative. The next step we need to do is to find our critical points. We know the critical points happen in two places. They happen when the derivative is equal to 0, and they happen when the first derivative is undefined. Since this is written as a fraction, I know the first derivative is equal to 0 basically when I set that numerator equal to 0. The first derivative is undefined when that denominator is equal to 0. And at this point, the calculus is over. Like this is now just a pre-calc problem, us solving some trig equations. So solving this one out, give me some more space. So the first one I can add 3, divide by the 4. So cosine squared is equal to 3/4. Cosine is equal to the square root of 3 over 2. For this other one, take the square root. We still have when is cosine equal to 0. And then now we can find our actual angles, which in this case is going to be our critical points. Cosine is equal to 0 at, of course, pi over 2. And cosine is equal to the square root of 3 over 2 in two places. Again, we do want to remember that this does have a restricted domain. So I only want answers between 0 and pi. Well, cosine does happen to be equal to either of those values twice there. that can be occurring at pi over 6 or at 5 pi over 6. So to remind you of what we have found that there are 3 critical points on the interval from 0 to 2 pi. I like putting them in order, so we had one at pi over 6, the next one was at pi over 2, and then the next one was at 5 pi over 6. So we found the critical points. Once we have the critical points, what can we do from there? We want to do the sign chart. So again, when I make the sign chart is a number line basically, and we want to find a sign chart for the first derivative. Go ahead and put your critical points in order, and they do kind of have to be in order. You're not going to get, like, your signs can just get messed up. This one is also unique because we're not going to have like from negative infinity or to positive infinity. So like I know it's just going from 0 to pi. So I'm just going to kind of put those there to remind me that I'm not going outside that range. And then I have my factors. I have this factor for cosine of x minus 3. And then I also have cosine squared of x. So we have 2 factors, the numerator and the denominator. And I can put vertical bars for the corresponding critical points. So the 4 cosine squared of x minus 3 gave me the over 6 ones. Cosine squared gave me the pi over 2. So again, I need to find where these are positive and negative. I like doing the easiest part first. Cosine squared is definitely easiest for me because cosine squared is always going to be positive. So now I just need to deal with this numerator. So some hints I will give you, because oftentimes when you're finding test points for trig, it can be a little bit awkward finding some radian measures. And I will say, as long as you're not plugging in a critical point that came from that factor, you're going to be good to go. And what I mean by that, I would not want to plug in pi over 6 into the 4 cosine squared of x minus 3 because I know I'm going to get 0. But you are perfectly allowed to plug in pi over 2 because pi over 2 did not come from that factor. Also, pi over 2 is a pretty easy one to use. I can also use those intervals as well. Like 0 and pi were not critical points, and 0 is kind of pretty close to pi over 6 to the left of it, so I can plug it in. Same thing with pi, it's pretty close to 5 pi over 6, just slightly beyond it. So I'm going to show you what I'm doing for that first interval. I'm thinking, what is this factor doing when x is 0? Well, the cosine of 0 is 1, so I have like 4 minus 3, which gives me 1. Again, I don't really care about the number, I just know that it's positive, so this interval is positive. This middle interval, I can go ahead and plug in pi over 2. The cosine of pi over 2 is 0, so we get negative 3, but the value doesn't matter, I just care is it positive or negative, and we do see that it is negative. And I can do the same thing at pi. The cosine squared of pi. Cosine of pi is negative 1, but I'm squaring it, so positive 1. 4 minus 3 is still positive 1, so I get a positive 1 here. And then I do want to find what the intervals are overall. Positive and a positive means it's positive. Negative and a positive, a negative and a positive, and then a positive and a positive. And then remember, you're bored of this because it's pretty straightforward. It is tedious, I think, but again, straightforward. Your answer is not the sign chart. You do need to justify your answers. So I can say that this was a function f of x. F of x is increasing on the interval from 0 to pi over 6, union 5 pi over 6 to pi. How do I know that's increasing? Because f prime is greater than 0 there. And I know that f of x is decreasing. Again, I'm going to write this as 2 separate intervals because pi over 2 is a critical point. So pi over 6 to pi over 2, union pi over 2 to 5 pi over 6. How do I know it's decreasing there? Because f prime is less than 0. Again, the calculus part of that problem is very, very small. Like finding the derivatives calculus and knowing the definition of a critical point is calculus, but like the solving and the sign chart is really stuff you can do outside of a calculus class. I know I'm cutting it towards the end of class, but are there any questions on that particular problem? Max.
This isn't a question really about the problem specifically, but more about how it will be used on like quizzes and tests. Are we allowed to like forego the sign chart and like solve it more logistically, or?
So you are technically allowed to do it any way you want as long as you're doing proper math. You just want to make sure if it asks you to justify your answer, you're able to justify your answer clearly and knowing those intervals. So like, no, you don't have to do the sign chart my way, but you just need to be able to get to the correct answer mathematically.
Okay, thank you.
You're welcome. Any other questions? Yes, Matthew.
Like you never had a denominator, like there's no way you could convert to denominator, how would you figure out like all the points?
So Matthew's question was, how can you find the critical points if it doesn't have a denominator? And that's a good question. So both the examples I did, there was a denominator. But if there is no denominator, then your critical points are basically only going to be where it's equal to 0. We just would never have a point where the derivative is undefined. So then you probably would have a simpler sign chart because it would have less points on it. And that's a good thing to bring up. Like the critical points do come where the first derivative is equal to 0 or undefined. You can have derivatives that are just equal to 0, and you can also have derivatives that are never equal to 0 and only undefined. And they're ending class here, so I'm going to go ahead and end it as well. The homework you can begin working on is homework number 1 from the textbook. We'll regroup tomorrow because I know today's notes were a little bit long. Tomorrow's notes will not be as long since it's basically the same but with the second derivative. So I will see y'all on Tuesday. Again, sorry that notes lasted so long. But yeah, see you tomorrow.